everyone, and thank you for joining us today. I am Marcello Bruno, an application engineer here at ENGISOFT. This is our second webinar regarding lithium battery technology. And let me say, it's a technology we strongly believe in here at ENGISOFT. The first webinar was about degradation. Today, instead, we are talking about the thermal runaway. That is a big challenge for everyone in this field. It's something we have to manage in order to avoid some catastrophic phenomena, such as fire or explosion. During this webinar, we are talking about both theory and a practical example. I said we because today with me we have Prajakta Sabnis. Prajakta is the co-founder of Urja Energy, a deep tech startup which uses a combination of physics and machine learning to perform predictive modeling of batteries. After completing her master from IIT Bombay, Prajakta worked at Multiphysics MNC for over 12 years, leading the application team since 2010. In today's presentation, Prajakta will cover background and physical process beyond thermal runaway, impact of cell usage and aging of thermal runaway, various triggers leading to thermal runaway, and Urja hybrid approach to capture, initiation, propagation, and device mitigation strategies. Instead, I will share with you a practical example. Hello, Prajakta, can you hear me?
Yeah. Hello, Marcello.
First of all, I want to thank you for being with us and for sharing your idea. But Prajakta, before moving on, I would like to give to our attendees a little bit of information about this webinar.
Sure.
So for question, you should see the Q&A toolbox in the Zoom window where you can write your question. Prajakta and I will answer all your questions following the presentation. Instead, tomorrow you will receive an email with 3 links. The first link is to watch again this webinar because we are recording this webinar. The second link is with the presentation of today's presentation, and we also will send you another link in order to see the video of the last webinar regarding degradation. So Prajakta, if you are ready, you can share your screen.
Yeah, sure. Thank you, Marcello, for the kind introduction. And good morning, everyone. Good morning and good afternoon, everyone. Just a second. Marcello, please let me know once you can see my screen. Is the screen visible or not yet?
Not yet.
Is it visible now?
Yeah. Thank you.
So as Marcello mentioned that in today's session, we will look details about the battery thermal runaway, why it happens, and what are the physical processes involved. And more than that, we will also try and understand that what are the kind of different mitigation strategies that one can have in order to prevent this thermal runaway or the thermal runaway propagation from happening. So as Marcello mentioned that the presentation that I will be having today, that I will briefly give you about the background, the approach what we use at Urja, few case studies and some validation cases also. And after that, Marcello will also take you through the app demo through which you will also get to know that how you can model this kind of problems in Urja. So interestingly, while preparing for this webinar itself, I came across this interesting study which is presented by this Clean Energy Associates, the report that they have published recently, wherein obviously it is mentioned that the fire risk is on high rise, and over there they have given a differentiation of what kind of defects are leading to the thermal runaway. And as you can see that the module manufacturing as well as the system level defects are the highest defects. So when we are talking about the system level, that is the pack level and the entire assembly, those defects are nearly around the 50%, whereas the module manufacturing defects are around 23%. So whenever we are talking about the thermal runaway, which is leading to explosions, they are occurring not just because of the cell level defects, we can say, but mainly because of the manufacturing defects which are occurring at system level, at the pack level, or at the module level, like how you are assembling the modules or the packs, how you are designing the modules or packs. what kind of cooling strategies that you are using in these modules or packs, that are mainly governing how the thermal runaway is going to happen inside these modules or packs. Over here also they have given different types of interesting differentiation, like for example, what kind of defects, like the component level defects or the enclosure defects or the manufacturing defects itself, which could be like, for example, when we are talking about the manufacturing, it could be how the welding has been done. Or so when we are talking about the enclosures, these defects are mainly how the casing has been done for your particular pack, and if there are any mishandling in the casing itself, or if the material that you are using for the casing is not appropriate, if that is causing the thermal runaway. So with all these studies, as you can understand that the thermal runaway propagation, which is leading to these fire incidents, it is not just because of the cell defects, because as we know that identifying a cell which is a defective cell, which is going to lead to a thermal runaway propagation, which is going to lead to the explosion incidents, it is very difficult to find. But what we can definitely prevent from happening is that if we can very well design the pack itself so that the thermal runaway propagation will not happen, even though there is any defective cell present in your pack. And that's what our today's overall discussion is also going to be. So as I was mentioning that we will, in today's webinar, we will discuss about that what causes the thermal runaway. So one is definitely, we know that one could be the manufacturing defects in the cells itself. Or it could be internal short circuiting or the external short circuiting. When you are talking about internal short circuiting, definitely it will also depend upon that how the cell has been used, how badly the cell has been also used, because of that also it might be leading to the internal short circuiting itself. And when we are talking about these different causes in the thermal runaway in the cell itself, the capturing this particular thermal runaway initiation in the cell is a big challenge, because it is unknown to anyone that what kind of defects are present inside the cell. From the outside, all the cells may look alike. They might be looking as a healthy cells itself. Whatever the signatures, the current voltage signatures that you are taking from the cells, the initial signatures, they may look similar to each other. But at the same time, some cells out of this lot might be a defective cell, and that because of that defective cell, it may get into thermal runaway under certain stressed conditions. And because of that one defective cell or the couple of defective cells, the entire pack may go into thermal runaway if the appropriate pack design has not been done. So when we are talking about this thermal runaway itself, so as given on the slide over here, that typically this is the ARC signature, that is accelerated rate calorimetry test, which we perform in order to understand the thermal runaway characteristics of the cell. This is how the ARC test data of any cell looks like. So in such kind of ARC data, there are three different temperatures, the important temperature profiles that one needs to look into. One is the T1, that is the onset of abnormal heating. So whenever a cell starts going into thermal runaway, as we know that first of there will be different types of reactions will start happening inside the cell itself, which are the exothermic reactions. And because of these reactions, there will be uncontrollable heating inside the cell, which will lead to the thermal runaway. So here in this case, this T1 is onset of abnormal heating. The T2 is actually the thermal runaway triggering temperature, we can say. And the T3 is the maximum temperature that a cell can reach during thermal runaway. Based upon these three different temperatures, these are the characteristics, signatures, or the temperatures, I would say, which any cell will exhibit, which will decide that how that cell's thermal runaway performance is going to be. So at any point of time, a cell gets triggered. It could be internal trigger or the external trigger. It means, for example, it could be some mechanical trigger or some short circuiting itself due to some internal defects as well, or it could be the external short circuiting happening because of some defects in the external circuitry. Any of these triggers, because of that, the cell will get into thermal runaway. And once a cell gets into thermal runaway, based upon how the pack has been designed, what kind of cooling mechanisms have been provided, based upon that, we can see that if the pack will undergo thermal runaway propagation or not. That means from one cell, it will propagate to other cells. The other cells will also start getting into thermal runaway, and slowly the entire pack will go into thermal runaway, due to which it will lead to explosions. So when we are talking about this thermal runaway itself, as I was mentioning that there could be various types of triggers present. So it could be the mechanical abuse itself, or the electrical abuse, or the thermal abuse, abuse as well, as shown over here. Because of these different types of abuse, it could be means first of all, it could be due to the internal short circuiting or the external short circuiting. And because of these various triggers, there might be certain, what I can say, the internals of the cells might be behaving differently. So for example, we know that whenever we are using cells under very cold conditions, and if you keep on using the cells in cold conditions like cold weather, like for example 0 or sub-zero temperatures, in that case, or with high C rates usage also, the lithium plating is going to be very high in the cells. Now, if you keep on using the cells with poor thermal management in such case, wherein rather than maintaining the pack at the higher temperatures, if you are maintaining the pack higher in the sense the 25 degrees or 35 degrees Celsius temperatures, if you are maintaining the pack and operating the pack around the 0 degrees Celsius, then in that case, the lithium plating is going to get accelerated. And because of that, whenever you are having the very high lithium plating, it may also lead to dendrite growth, which will also lead to internal short circuiting also. So there could be various reasons because of which the thermal runaway may happen. And because of that thermal runaway, because of thermal runaway happening in a cell, it may also cause thermal runaway propagation in the pack itself. So as I was mentioning, there are three different temperatures or the characteristics temperatures which are present in any ARC signature or the thermal runaway signature of the cell. So at T1, that is the first temperature I was mentioning over here, which is the onset of abnormal heating. At T1, the ACI layer decomposition starts. Then at T2, as mentioned here, which is the thermal runaway triggering temperature, the ACI layer breakdown happens and the electrodes, cathode and anode, get exposed. After that, at T3, that is the maximum temperature at which the actual cell reaches to this maximum temperature during thermal runaway, the main heat release due to the redox reaction happens, and that's when the cell reaches the maximum temperature during the thermal runaway itself. So as I was mentioning, even because of the degradation also, there might be some certain thermal runaway. The degradation also would be affecting the thermal runaway signatures. So as earlier I was mentioning that there are three different T1, T2, T3 temperatures are present for any given cell. These are the characteristics temperatures for a cell. So typically this T1, which will be around, which is the onset of self-heating, this is around 70 to 90 degrees Celsius. Whereas we are talking about T2, it is around 140 to 200 degrees Celsius itself. And T3 is actually the maximum temperature at which the cell will reach during thermal runaway. Now, as we know that at T1, certain type of reactions start. Then at T2, again, the both electrodes get exposed. And because of that, the cathode reactions also start. And then at T3, oxygen reacts with electrolyte, and then the cell reaches to Tmax. Now, as we can see that T1 and T2 are the critical temperatures. One is below 100 degrees and the other one is somewhere around 140 to 200 degrees Celsius. Now, what happens that because of the aging, how the cell is being used, and when the cell starts aging, like 300 cycles, 500 cycles, or 1000 cycles, so on and so forth. Due to the aging itself, these temperatures, the T1 and T2 temperatures start coming down. And because of that, what happens that earlier the cell could withstand, let's say that up to 90 degrees Celsius thermal load. It may stand just the 70 degrees thermal load itself. And after that, some self-heating reactions will get started. That means the cell will be more susceptible to the thermal runaway phenomena as and when it starts getting aged. How much it will get affected, it will depend upon that, how the cell is being used, how it is getting aged, and what kind of dominant degradation mechanisms are present in that cell, which will be based upon the usage of the cell itself. So this is one, I would say, the diagram which is shown in the slide, which will give you a fair understanding about that what type of degradation modes are present in the cell and how they are affecting the thermal runaway performance in the cell itself. All in all, as you can say here, see here, is that because of the degradation, the thermal stability of the cell reduces, because of which the temperature rise rate increases, and hence the next challenge is that T1 and T2, that is when the self-heating reaction start and the thermal runaway gets triggered, both the temperatures come down, and because of that the thermal runaway can get initiated at the earlier stage than getting initiated, let's say, around 90 degrees or around 140°C itself. So as till now, what we were discussing is that how thermal runaway may get initiated in the cell itself. But as we know that having just thermal runaway in a single cell is not going to lead to the explosion, because we do not, practically speaking, one cannot have control over which cell is a defective cell and whether that cell is going to lead to thermal runaway or not. What is more important to understand that if in a pack, if any cell, whether it is a center cell or the corner cell, if it is a rogue cell or the defective cell, and if that cell gets into thermal runaway, we need to understand that if the rest of the pack is also going to get into thermal runaway or not, if the propagation is going to happen or not, and how we can prevent that propagation from happening so that it will not lead to any explosions. So here in this case, as I have shown, so let's say that this central cell is a defective cell, and as you can see that slowly that cell itself means once it gets into thermal runaway, slowly it starts heating up the neighboring cells also, and the other cells will also start going into thermal runaway. And if that happens, definitely it may lead to the explosions also. So now when we are talking about the means thermal runaway propagation, it is also important to understand that how this different cell chemistries as well as the thermal runaway signatures at different SOCs, how do they look like. On the left hand side, as you can see over here, I have shown these TR signatures for LFP, for an LFP cell itself. The measurements are done at different SOCs, wherein you can see that as and when you are having the cells which are kept at the higher SOCs or very low SOCs, the thermal runaway happens quickly as compared to if you are storing the cells at, let's say, 50 degrees, 50% or the 75% SOC. So this also you can correlate it to the recent incidents or the accidents that we could see, wherein few vehicles which are kept in the during the transportation itself, the few vehicles caught fire. Probably one could also see that at what SOC the battery was kept, whether the battery was stored at the higher SOC, because of which the batteries caught fire or not. So these temperatures and the SOCs will also give us an idea that how the batteries should be stored, how they should be transported, so that we can minimize the risk of the thermal runaway as well. When we are talking about the effect of or the impact of SOC, we can also get to see that how the thermal runaway gets impacted based upon the form factor as well as the different chemistries itself. And for that, I have given one comparison between the NMC and the LFP cell itself. So here, as you can see that the LFP cells get into thermal runaway much at the later stage as compared to the NMC cells itself. At the same time, the maximum temperature, if we are looking at the cells, the maximum temperature reached by the LFP cell is also comparatively less than if we are comparing to the few other NMC cells. So historically speaking, people, they definitely say that the LFP cells are comparatively safer than NMC cells. But the recent study has also shown that even though we say that the LFP cells are having lower lower Tmax, that is the maximum temperature reached during the thermal runaway, at the same time, these LFP cells generate more smoke, and because of that, they are more susceptible to the thermal runaway propagation as well. So, as and when we are using different types of chemistries, even though we get to see that the Tmax is low or let's say the T2 is higher, that doesn't mean that the propagation will be prevented. what is going to prevent the thermal runaway propagation, how well you are going to design the pack so that the heat transfer can be, or the heat losses can be increased, and the heat transfer from one cell to other cell can be minimized, so that the thermal runaway propagation itself can be avoided or can be minimized. So for that, from that point of view, if you start looking into how the thermal runaway mitigation can be devised. So for example, at the cell level, one can have the temperature resistant separator or the coated separator also, which will help increase the thermal runaway trigger temperature itself. Or one can also have some anode and cathode coating, again, because of which the time required or the temperature at which the electrodes will get exposed, that will also can be increased. Or one can also add additives itself, which will also help us take the T1 temperature, that is the self-triggering temperature itself, to the higher level. But as we know that the manufacturing or the modifying the cell parameter itself may not be in our hand. Most of the times, many of you, as I understand that, you might be buying the cells directly from the cell suppliers. And then by using those cells, you would be building your modules or the packs, which will be used for your specific application. And hence, at that case, in that case, what we can do is how we need to understand that what kind of system level modifications that we can make in order to get the thermal runaway preventions. So here in this case, we can add certain thermal barriers. So for example, you can have, let's say, the thermal pads also can be inserted in your pack, or it could be like some microchannel plates also can be, cooling plates also can be introduced, so that it will take away the heat from the pack, and it will ensure that even though one cell gets into thermal runaway, the thermal runaway doesn't get propagated further. Or you can also have the BMS to drain the SOCs of the adjoining cells. So for example, in the previous slide itself, we were seeing that if the cells are at the higher SOCs, the chances of those cells going to thermal runaway will be higher because of the thermal runaway signature at the higher SOCs. So in that case, whenever, as and when the BMS can detect that one cell is going to thermal runaway, it can ensure that the neighboring cells, it is reducing, or it is draining the SOC of the adjoining cells, so that you are reducing the risk of those cells getting into thermal runaway. So having said this background, that how to understand the thermal runaway in cells as well as in the pack itself, now let's understand how we can model thermal runaway in Urja. So, as few of you might have attended our previous webinar as well, wherein we discussed in detail our approach. So, in Urja, what we do is that we use the hybrid modeling approach, wherein we combine the physics-based models with the feature-based machine learning or the data-driven models in order to get the faster, accurate, and the more reliable solutions itself. So, for example, when we are talking about the thermal runaway modeling, we use the ARC test data, wherein we use the standard heat wait seek protocol. So, what we understand that if we go for the thermal runaway modeling with the traditional way, wherein the pure physics-based models are used, one needs to know all the side reactions, how those reactions are happening, what are the coefficients are involved, what kind of materials are being used inside the cell itself in order to model the entire thermal runaway phenomena in a cell. But as we know that most of the time we do not get access to the internals of the cells itself. And hence modeling the thermal runaway initiation is a big challenge if we are doing it with the traditional physics-based modeling way. So at Urja, what we do that we use the data-driven physics-based models, wherein we use the ARC test data, that is accelerated rate calorimetry test data. And by using that test data, we characterize the cell for the thermal runaway. That means we estimate the various parameters defining the thermal runaway in the cell itself. And once those parameters are estimated at the cell level, we build the entire path in Urja. And once that pack has been built, we can understand that how the initiation, thermal runaway initiation and the propagation happens in the pack itself. And so for that, the ARC data that we use, it is a standard heat wave seek protocol. ARC data is used. As many of you must be familiar with this ARC protocol. Here in this case, the cell is forcibly taken into thermal runaway state itself by applying a small heater power in small steps, which is typically taken as 2 degrees Celsius per minute. After that, once the heat is applied, there will be certain wait period in order to let the cell reach the isothermal equilibrium itself. After that, the seek period is given, wherein it will detect the heat released by the temperature rise itself. So with this heat wave seek protocol, it will try and check that how the cell is getting into thermal runaway itself. And for that, the instrument will be recording the temperature versus time data along with many other parameters itself. What we need in Urja is that mainly the temperature versus time data along with the exotherm data. Exotherm data is nothing but the data which is collected from the TR trigger point to the maximum temperature reached by the cell. With these two data sets, we can extract the useful information which is required to build the cell and the pack level thermal runaway. So this is one of the validations what we had performed on for the ARC test data that we had used. So here in this case, once we get the thermal ARC data in Urja, as I was mentioning, we estimate the different parameters responsible for the thermal runaway inside the cell itself. Based upon that, the thermal runaway heat source calculation is also done. Like for example, the thermal runaway happens in the 2 stages. It could be like the heat source at the stage 1, wherein the ACI decomposition as well as the lithium reactions with electrolyte at anode interface may happen. Whereas in the stage 2 reactions, there could be many other multiple reactions like electrolyte decomposition, cathode material decomposition, so on and so forth. So essentially what happens that at these different stages, there will be exothermic reactions will start happening. First of all, the stage 1 reactions will start happening, because of which the self-heating of the cell will happen. After that, the cell will slowly, because of this self-heating of the cell will reach to the T2 temperature, which is the thermal runaway triggering temperature. At T2 temperature, additional exothermic reactions will start happening, as mentioned over here, like electrolyte decomposition, internal short circuiting, etc. And because of that, there will be uncontrollable heat will get released by the cell itself, due to which the cell will get into thermal runaway. So as you can see that the total heat source because of the thermal runaway is combination of this stage 1 and the stage 2 reactions itself. And by using this total heat source, we will be solving for the heat diffusion equation inside Urja. So with that, once we start building the model, we can first of all try and understand that how well we are capturing the thermal runaway signature of the cell itself, wherein you can see that if this is the ARC data, what we have used as an input to the model. In the pack level analysis, we can also try get the accurate capturing of the onset of the thermal runaway. So as and when the cell hits the T2 temperature, after that the stage 2 reactions also start, and because of that the accelerated heating will also start happening inside the cell itself. Not just the thermal runaway, means how we are capturing the onset of thermal runaway and the thermal runaway triggering temperature, etc. We also capture the gas venting during thermal runaway. So here in this case, as you can see that as shown on the slide itself, we model the thermal runaway, the gas venting during TR at the cell level, for which we provide the commonly used electrolyte solvent library inside the tool itself. And by using that library for data or your own electrolyte solvent data, you can model the gas venting during thermal runaway. So in order to model these different phenomena, we are having different products available in our app as well. The app what we are having is app.urja.energy. It is hosted on our server. And through that app, you get access to these different apps. One with starting with the material app, wherein the entire, you can create the repository of the cell and the pack materials, or the data app, wherein we import the experimental data and clean up the data, which can be used for the further analysis. As I was mentioning, we typically deal with these hybrid models wherein we directly use easily available experimental data to augment our physics-based models also. So in that case, cleaning up the data is an important step before we start using it, and that has already been provided in the data app. Then by using design app, you can create any type of complex design inside Urja itself. My colleague Marcello will shortly show you that how you can create these designs also quickly by considering all the pack level details as well as the connectors, different cooling strategies, etc. Then considering today's topic means essentially I would say that we are also having an heat app through in which you can you can create your cell level as well as the pack level models, wherein by using let's say HPPC data, ARC data, you can model the entire thermal model as well as the thermal runaway initiation and propagation at the pack level as well. So by using this product, we have created one small case study wherein we use this NMC 21700 4.8 ampere hour cell itself. The configuration is very simple. That is a 5S 6P single layer pack was constructed without having any enclosure in it, and wherein the cell to cell gap was considered as 3 mm was the initial case. Now, the same pack we modified for the two cases. One was like if we are using the pack with cell to cell gap as 0.75 mm without any enclosure. And if this cell is considered as a defective cell, so in that case, we wrapped a heater around that particular cell and then took that particular cell into thermal runaway. The objective of this study to understand that if this cell is going into thermal runaway, if the rest of the cells, the neighboring cells are also going to get into thermal runaway or not, if the initiation happens or not. And because of that, if the entire cell, entire pack also gets into thermal runaway or not, that propagation also happens or not. So here in this case, with this study, you can see that all the cells go into thermal runaway because there isn't any cooling mechanism provided. It also doesn't have any spacing. It doesn't have any casing also available, so that there isn't any kind of basic heat sink is also not available in order to take out the heat from the pack. And hence, because of that, you get to see that slowly all the cells start going into thermal runaway and the entire pack also undergoes thermal runaway within 1 hour itself. Now, in order to avoid this thermal runaway propagation, the modifications that we have done, I will just discuss in the next slide. I forgot to mention that we also studied that rather than having this corner cell as a trigger cell, if we are, let's say that if we are considering the different cell locations as the defective cells, how the thermal runaway response of the pack looks like. And as you can see over here, based upon which cell has been triggered, you can see that the percentage of cells going into thermal runaway. Obviously, the cell 13 is somewhere around center, and whenever we are having center cell going into thermal runaway, the total number of cells undergoing thermal runaway are the 100%. That is, the entire pack went into thermal runaway. So this is the kind of what if analysis you can easily perform using Urja, that considering that defective cell location and based upon that how the thermal runaway propagation happens, and then make the design modifications in order to prevent that from happening, like we have done here in this TR mitigation study. So what we did was we used the same pack, but here in this case, rather than having without casing pack, we included some 5 mm thick conductive enclosure itself. And then because of that, you can see that the pack, even though a defective cell undergoes thermal runaway, the rest of the pack is saved. The rest of the pack doesn't undergo thermal runaway in that case. So this is how you can also prevent the entire pack undergoing thermal runaway by making the design modifications. Here in this case, just the conductive casing is used, but in your case, it could be the thermal pads you might want to use. You might want to use some end plate cooling or some forced convection also. Different type of cooling strategies one can devise using Urja. So apart from that, another means one nowadays popular technique in order to prevent thermal runaway is to use the phase change material. So Urja also supports the modeling phase change materials inside the pack. So here in this case, you can see that this is the air cooled pack without having any PCM, wherein all the cells undergo thermal runaway. Whereas when we started using PCM for this particular design, you can see that the thermal runaway got delayed based upon that the cell to cell spacing used. We have also seen some customer use cases wherein they used this PCM inside the pack, and because of that they could get rid of thermal runaway altogether based upon obviously the pack design what they are having along with the phase change materials itself. So Urja supports these thermal runaway initiation propagation models not just in the cylindrical cells but other form factors as well if you want to have the pouch cells or the prismatic cells also. So one of such cases I am just presenting over here is the prismatic module, that is the 12S1P module, which was done for the 37 ampere hour cell. And here in this case, we compared our results, Urja results, with the published experimental data itself, wherein we could get the qualitative match with Urja results and the published literature, wherein all the cells are going into thermal runaway, and even the thermal runaway propagation rate also could be measured. When I mentioned the qualitative match, because the data, the design details were not available in that paper, and hence we could do the qualitative match over here. But you can see that the physical trend as well as the qualitative match can be seen easily over here. As I was mentioning earlier, for the gas venting also, for the gas venting models also, we have done the validation in terms of like how much heat, that vented heat obtained from Urja is same as the vented heat given in the published literature as well, when the cell venting was modeled along with the thermal runaway models in Urja. So with this means I would request Marcelo to show you the Urja app itself and discuss how the model, what I discussed just now, can be built easily in Urja.
Thank you,
So,
Prajakta. Thank you very much.
Yeah.
May I share my screen?
Yes, yes.
Thank you. Prajakta, can you see my screen?
Yes, I can see your screen.
Okay,
Thank you.
perfect. As you can see, this is how Urja looks. This is a graphical user interface. On the left, we have two windows, My Spaces and Shared Spaces. Of course, we can share our project with our colleagues or also with external companies. In this case, we are going to see this project. As you can see on the left, we have 8 apps: material, data, volt, design, range, heat, feed, analyze. During this demo, we are going to see material, data, design, and heat. The first one is material, and as Prajakta told us before, is to create the cell, to create the pack, and in other words, our database. So about the cell, the first property we have to define is the positive electrode, and we can choose between LFP, NMC, NC, and LSCO. In this case, in our demo is NMC. About negative electrode, we have graphite. In this case, the cell nominal capacity is 3 ampere hour. We define a cylindrical type, but we can also customize our geometry. We can also define other properties such as density, specific heat capacity, and emissivity, but also thermal conductivity. After the cell, we have to define some feature. We can define some feature about a battery pack. In this case, we have enclosure, insulation, filler, PCM, thermal pad, and plate, connector, and separator. During this exercise, we will use enclosure, aluminum enclosure, and connector. About aluminum enclosure, we have to define some properties such as thermal conductivity, specific heat, and density. About the connector instead, we have to define cell-to-cell connector properties and terminal connectors. And for both of them, we have to define density, specific heat, thermal conductivity, and electrical conductivity. Then we can move to the app data. Here we have on the left 5 kind of data we need in Urja, and the design import, of course. About heat, we need this kind of data, arc test, as Prajakta described us before. In this, for arc test, we have to define some parameters such as heat period, wait period, seek period, initial ambient temperature, max ambient temperature, and temperature speed. On the right, we can see, I want to show you 2 graphs. The first graph is this one, temperature, and it's just about temperature versus time. And this graph about the data we added before. We can also add exotherm temperature data. If we have it, it will improve our results. The second graph I want to show you is this one, is temperature rate. It's just temperature rise rate versus temperature. At the beginning, we have some floating results, because in this period, at the beginning, we have a heat period and wet period. And so this is why we have this floating graph. The next step is design. With Prajakta, we define two cases. The first case is to have thermal runaway. The second case is to avoid thermal runaway. So basically, they are very similar, but in the first case, we don't have enclosure, and we have a very small gap between cells. So the first I want to show you is the design with the battery pack with thermal runaway. As you can see here, we selected the cell we want to use. Cell connection, in this case, we have 5 cells in series and 6 cells in parallel. The battery pack is grid, and we define just one stacking layer, and we have 5 cells in X direction and 6 cells in Y direction. In this case, cell-to-cell gap is 0.75 for both X direction and Y direction. Also, as I told you before, we don't have in this case enclosure, thermal pad, filler material, separator, and plate. Filler material in this case is just air. About connection, it's very easy to create the battery pack. We have to define here the material connector here. And so in order to connect the cell, it's very easy. We have just to click on it, and automatically we can define the parallel connection, positive terminal connection, and connection to P1, and so on for P1, P2, P3, P4. Here we have some tool to see our battery pack. For example, I can add the filler. I can explode my battery pack. I can rotate, of course. And then now we can move to results about thermal runaway. And we have, as you can see, we have training model and prediction models. The training model, and here we can create our model. And then in prediction model, we will use this model in order to get our results about the thermal runaway. So we can go deeper about the training model. As you can see here, we have to select once again the cell we want to use, and automatically Urja fills added every properties. So NMC, graphite, the cylindrical properties of the cell, and geometry cell. And also we have to define training data. In this case, we use the APPC data, and for example, this kind of data. And for thermal runaway, we use, of course, the data we added before. So in this case, this data we added here. Then we can move to the results. And the first case is with the thermal runaway. So once again, we define the model we want to use, the battery pack with no casing in this case, the cooling strategy. So in this case, we have natural convection. We want to perform thermal runaway propagation in the pack. Heater, we have to define which is the cell we want to heat. The cell initial temperature, and in this case we added a database in order to define the heater power. We can also include the venting effect, but in this case we didn't. We can also add the drive cycle, or current versus time and power versus time. In this case, no known drive cycle. We performed our prediction for around 3,600 seconds. The test condition is initial COC at 0.9, and pack initial temperature is 50. mesh refinement is fine, and other ambient temperature. Now we can move to results. And I want to show you two graphs. The first graph is, as you can see, we have thermal runaway propagation. So the first cell went to thermal runaway, and so the propagation started. The second graph I want to show you is heat map, and as you can see, is the temperature inside the all the cell of the battery pack. We can see different time just by clicking here, and so we can understand how the propagation is going on. We can move back to the second case, and this is the second case, and is the same it has the same parameters as before. We just modify cell-to-cell gap. In this case is 3, and we added enclosure, aluminum enclosure. So we come back to it, prediction model, and we can go to no propagation model. So everything is the same. Training is the same as before. And we modify the battery pack, of course, but the other properties are the same. So the same number of seconds we want to perform, the initial COC, the initial pack temperature, and the same cell to heat. Everything is the same. So we can go to results. And as you can see, in this case, the first cell went to thermal runaway, but we don't have thermal runaway propagation because we modify the gap. The last graph is about heat map. And as you can see, once again, we can see the temperature during our simulation period. And as you can see, we don't have any propagation. So Prajakta, this is one of the challenges we can perform with the Urja, but we can also provide other situation we have to manage with Urja. So can you?
Sure. Thanks, Marcelo. So as Marcelo discussed just now, that one approach of modeling thermal runaway is you are providing the external trigger, that is the external heater itself, due to which the the rogue cell can get into thermal runaway. The other way how people also want to model is that when the battery pack is in operation, like you are supplying certain current or you are drawing certain current, and during that loading or charging itself, because of high load current or the high charging current, like fast charging, which may happen in very high ambient temperatures also, like during summer days or so. Because of this combination itself, the pack may undergo thermal runaway. So those kind of situations also can be easily modeled using Urja. Or you can also try and you can just decide that if the pack is just kept, which is not being used, it is just kept in very hot environment, and because of that, if it is going to get into thermal runaway or not. So there are various different ways in which you can model thermal runaway in Urja. Yeah. Marcelo?
Prajakta, can you share your screen, please?
Sure. Definitely. I will share my screen. And before that, Marcelo, I think we should also go through the questions. I see that there are quite a few interesting questions that we have received. So if we can take them before we go back to the presentation.
Okay. Prajakta, do you expect to see the impact of connector design on the thermal runaway signature of the pack?
Yeah, thanks. That is a very interesting question. And absolutely. The connectors do have impact on the thermal runaway signature. So before going for the thermal runaway also, as we know that based upon how the connectors have been designed or how the connector properties are, it is going to have the impact on the overall thermal signature of the pack, whether it is going into thermal runaway or not. If you are having, let's say, the connectors wherein the contact area is very, let's say, very small itself, or if you are having connectors with a very high contact resistance, for example, because of that, you are going to see the high temperature rise just based upon the connectors itself. And as we know that there are different ways in which these connectors, especially the series connectors, are designed in order to reduce the total amount of heat generated due to the connectors itself. And as we get to see the huge temperature rise due to the connectors, definitely they have a great impact on the thermal runaway also. So if means just a case study itself, if you want to perform, one can see that with and without connectors, how the thermal runaway signature looks like. And over there, you will get to see that with connectors, the temperature rise is much higher, as well as the pack also gets heated up easily and quickly. And all these cases can be easily modeled in Urja.
Thank you, Prajakta. The next question is, how does aging affect the thermal runaway of the pack? Any recommendation to address this?
Yeah. So as I mentioned in the previously in the presentation itself, that because of the aging, the individual cell's thermal runaway signature itself gets affected. Like for example, one can get to see that the thermal runaway trigger temperatures or the self-heating temperatures also get affected. They get reduced, and because of that, the cell, which is otherwise safe up to, let's say, 100 degrees Celsius or the 140 degrees Celsius, the cell will be susceptible to thermal runaway at the much lower temperatures. And that way, as the cells are getting affected, obviously the neighboring cells also will get affected, and the packs, the probability of the pack going into thermal runaway also increases with aging. So when we are saying that any recommendation, one of the recommendation is obviously, like for example, as we know that one of the aging effect is the lithium plating, and because of the very high lithium plating, it is going to lead to internal short circuiting as well, for example. So normally, one should not be using the battery pack at the 0 degrees or the sub-0 degrees temperature. So as we know that even the battery packs cannot be used at very low temperatures or very high temperatures. When I say very low and very high, that means anything beyond 20 degrees Celsius, below 20 degrees Celsius, or anything beyond, let's say, 30 degrees Celsius also. Both the things are going to affect the aging of the cells. When we are considering the thermal runaway, the aging which is going to happen at the lower temperatures, that will be more impacting thermal runaway phenomena more. So in those cases, what we recommend is that, or what the industry practice is also, that one should be having a very good thermal management system, due to which one can keep the pack operating at around 25 to 30 degrees Celsius itself. So for example, that means in a colder environment, you need to have the appropriate heaters installed in your pack, which will reduce the lithium plating phenomena happening in your pack itself. Whereas in the hotter environments, one should be having the thermal management in terms of the cooling provided, so that it will reduce the pack temperature and will maintain it at the 25 degrees. So it all depends upon that, how well you are designing the thermal management system in order to maintain the pack at that sweet spot, I would say, which is around 25 to 30 degrees Celsius.
Thank you, Prajakta. The next question is, how many samples should be tested with ARC method in order to have a reliable database for the Urja TR model?
Yeah. So the method what Marcello showed today, over there we need the worst case scenario wherein we recommend having the single ARC data for the 100% SOC itself. Yeah. So that data is sufficient in order to understand how the thermal runaway propagation is, initiation and propagation is going to happen. And as I'm mentioning, it is the worst case scenario. That's what we are modeling then. But soon we are also coming up with some other apps which will also help you qualify the cells in the beginning itself. But maybe we can discuss sometime in the next webinar itself, or if you are interested in understanding how the cell qualification done for the thermal runaway signatures, definitely you can get in touch with Marcello also, and we can have that discussion further.
Thank you, Prajakta. The next question is, can custom geometries be made? Can I superimpose two cell modules and simulate thermal runaway on the bottom plane?
Yeah. Yes, definitely. One can create the custom geometries also. So the one example what we showed was the standard square pack. But there are certain techniques given inside Urja itself, wherein you can create any arbitrary shaped pack itself. You can have the multi-layer pack also. And in that multi-layer pack, then you can decide that, okay, which means cells in which layer will get triggered and how the thermal runaway is also going to happen.
The next question is, did you also model radiation in this, or the heat only gets transferred through the bus bars?
Yeah, thanks. Yeah, this is also important question, because as we know that during thermal runaway, the temperatures are going to rise very high, and then the radiation becomes important in order to capture the thermal runaway phenomena accurately. And Urja does account for the various heat transfer mechanisms. And when we are modeling thermal runaway, automatically the radiation also gets triggered, and it will also be accounting for the radiation phenomena for the thermal runaway modeling. So it will not be just the conduction. So radiation will be accounted for.
Thank you. And how and if Urja's thermal runaway analysis is different and better than just modeling thermal propagation?
Yeah, this is definitely an interesting question. See, when we are modeling just the thermal propagation, right, or the, I would say that in simpler words, it is the heat transfer model only we are considering then. So in that heat transfer modeling, we are not accounting for how the different, what I can say, the exothermic reactions are getting started in the adjacent cells. And because of those exothermic reactions, how the heat sources are also getting triggered or getting added at various point in time based upon the temperature at that point in time. So if we do not account for these heat sources, additional heat sources, because of the additional exothermic reaction, then we will not be able to model the thermal runaway problem accurately. So when we are talking just about the thermal propagation, then additional heat sources or the self-heating or the exothermic reactions don't get considered. What one would be doing that, whatever the available heat is there in the system, how that heat is getting propagated, that itself will be modeled, and that will be just the plain heat transfer analysis. But what Urja does is that Urja also calculates additional heat sources at each and every point in time to understand that how the different side reactions, how the different self-heating or the exothermic reactions are happening in the cells. Thereby, it also accounts for the initiation of the thermal runaway and then accounts for the thermal runaway propagation.
Thank you. The last question is, what about different NMC chemistry like NMC 622 or NMC 811? Is there a way to define this difference as well?
Yeah. So, see, means in Urja, when we are talking about using different, what I can say, the material composites like 622 or 811, etc., we directly use the cells data itself, the measurement data. Whatever the properties that you provide in our cells or the advanced settings, we can just show you later as well. Over there, those properties are provided as an initial guess. So for example, if you are going to perform this thermal runaway analysis itself, then in that case, we are uploading the cell's own signature. Then if we are modeling the plain thermal management problem without thermal runaway, we are using your cell's own HPPC data, DCIR data or so. If the degradation is being modeled, we use the actual aging data. So what I mean to say that even though we do not ask for the specific variant of the NMC itself, we use the actual cells data in order to extract the required information for the models in order to differentiate between the samples to samples or the chemistries to chemistries as well.
Thank you. Another question. Can I ask if the composition of the gas can be taken into account during the simulation? If yes, which data are necessary?
Yeah, so here in this case, currently we are not accounting for the composition of the gas. Means we do not give that as a separate different composites as in the output. But soon we will also be accounting for that, and definitely we'll then get back to you on that part.
Thank you, Prajakta. So I think we have almost finished the webinar. So if you want to add something, Prajakta, or
Sure. Just maybe a minute itself, I will just discuss. I hope my screen is visible.
Yeah.
Yeah, so thanks, Marcelo, for giving the demo also, and thanks. Those are the wonderful questions. So before we end the session, I thought I would just give a brief idea about what we offer in Urja. One is definitely, as we were discussing about the thermal runaway modeling in Urja. But apart from that, Urja has the entire suite which can be used at the various stages at your product development, wherein one could be like the cell design and performance, that is at the cell qualification itself, wherein when you are trying to identify which should be the supplier, because as we know that even though we know the, if you might have zeroed down that which chemistry that you want to use or which amp hour cell that you want to use, various supplier might be providing the same type of cell itself. How to decide that which quality of the cell is going to give you the required performance in terms of thermal stability, thermal runaway, as well as the warranty estimations or the degradation predictions also. So at that stage also one can use this cell qualification, or even while deciding which chemistry to go with, one can use it. The next is battery pack. As we were discussing earlier, one can use the battery pack design, analysis, thermal management system analysis using Urja. Again, means in many cases, people use the Urja's thermal runaway models before even applying for any certifications test to understand that their design is good enough, which will pass the certification test that they are applying for. The next is, as I was mentioning, for the warranty estimations, wherein one would like to understand that you are getting certain information from the supplier about the cycle life, but that will be the lab condition. That information will be given based upon the lab test itself. But in real life, based upon the actual duty cycle, drive cycles, the weather conditions, temperatures, or the fast charging, etc., how the capacity fade and the power fade is going to happen. Based upon that, the warranty also can be determined. Next is even the BMS. As we were discussing, the BMS also plays an important role when you are trying to mitigate the thermal runaway also, and hence it is very important to understand what kind of signals are sent by the BMS. So deciding the controls input for the BMS itself in terms of temperature, current, or we have also performed certain POCs wherein we have developed machine learning models which are trained using the physics-based models through which one can understand that even when you are having the limited sensor available in your vehicle, it will also help you understand actual thermal signature of the pack for the remaining cells wherein the sensor is not available. And because of that, the BMS can provide you the accurate signal also. And even the fast charging, because the fast charging is going to have an impact on the thermal signature as well as overall aging also, which will in turn impact your thermal runaway phenomena also later point in time. So all these different what I can say, the applications, battery related applications can be easily done in Urja. So if you are interested, definitely you can get in touch with Marcelo, and we would be happy to discuss this in on this further. So Marcelo, over to you, please.
Thank you, Prajakta, for your presentation and for your time. So if you want any other information, don't hesitate to contact me. As NGSoft, we support Urja to distribute their product in Europe. So don't hesitate to contact me. So Prajakta, and thank you once again for your time, for your studies, and for sharing your presentation. Thank you all for joining us for this meeting. So Prajakta, do you want to ask something, or?
Yeah. Thanks, Marcelo, for the wonderful webinar today, and thanks a lot all for joining us today and for the interesting questions also. I hope you found the webinar interesting and useful. And as Marcelo mentioned, please let us know if you would like to discuss this further. We will definitely be available.
Yeah. Once again, I remember that tomorrow we will send you an email with 3 links. The first link for the webinar, the second link for the presentation, and the third link for the last webinar about degradation. So have a nice day. Thank you all.
Thank you.